Hello. In this session, we are trying to solve one of the simplest problem in quantum mechanics called particle in infinite square. Well, so we have already discussed the foundations of quantum mechanics, the principles of quantum mechanics, what is wave function and what is Schrodinger equation and what is also called the stationary states. And we discussed what is the strategy and what is the algorithm to look at a quantum mechanical problem and try to arrive the solution. So we are trying to apply all those knowledge in this class and try to solve a very simple system called the particle in infinite square well or free particle in one dimension well. Okay, so before going to the exact quantum mechanical system, we can consider a simple classical system as shown in figure. So the figure shows a hill valley system with a wheel is rolling between this hill and valley. So the top of the total height, the maximum height of the wheel is h, and the wheel is moving with some initial speed v. And here we assume that the kinetic energy, the initial kinetic energy of the particle of the wheel, if it is much less than the total potential energy of the maximum potential energy of uh, the the hill, the hilltop. Okay, so obviously this wheel could not able to cross this maximum height, so it will just move between some certain position within the valley. Okay, it will move around the valley, and this is will be a kind of oscillatory movement in the absence of any kind of friction. Okay, so if there is no dissipative force, this wheel will roll between two locations. Maybe this location I can write minus a, and this location can be plus a, and the center can be written as 0. So the wheel will move around between the point a and minus a forever if there is no dissipative forces. Okay, in the absence of dissipative forces, this is what is going to happen. Now this wheel is not a free wheel because it is experiencing gravitational force at every moment, and the gravitational force, it will be minimum at the location of at this origin, at the minima point of the valley. And this force would increase if you are going away from the valley, and this force we can usually call the restoring force, and it is will be proportional to the displacement for a small displacement, obviously. Okay, so this kind of things you might have discussed during the chapter of oscillations in your undergraduate studies. Okay, now we are going to modify this problem a little bit. Now here from the first hilltop to the second hilltop, the height of the hill is gradually changing. It first it decreases to minimum, then it increases. Okay, now let us suppose if somebody has taken the portion of the hill in such a way that the hill become like this. Okay, suppose this valley become a completely flat ground. Okay, and the same wheel is now rolling with some initial speed. Okay, now what would happen to this wheel? So will it be able to climb the hill as in the earlier case? In the earlier case, it is climbing the hill for certain amount of height and it comes back. But what would happen in this situation? Okay, so in this situation, it will obviously will bounce back from both boundaries. From both boundaries can bounce back because it cannot have the much energy to overcome this barrier and reach to the other part. So obviously it will be bouncing back. Suppose this collision is elastic. If both collisions are elastic, then the kinetic energy of this wheel will remain same. So it will move with the same speed over and over and again through this between two of this barrier forever. in the absence of any kind of dissipative force. So in the earlier case, it was an oscillation. That oscillation is simple harmonic oscillation. Now this is again an oscillation. This oscillation cannot be treated as simple harmonic because there is no restoring force involved in this case, because it experiences force only at the boundaries during the ball, during this wheel collides with the wall. It experiences some momentum change, it experiences some force. After that, the speed and velocity of the particle will remain same until it experiences the next collision. So during this collision, what will happen? This ball, which is moving with speed u, it will become minus u during the collision. Okay, that is what is going to happen during the collision. Its momentum changes, it experiences a force, and after that, it will move the same speed. So it is not simple harmonic oscillation. So in case of simple harmonic oscillation, the speed must change with time. So it will have the maximum speed at the equilibrium position and minimum speed at the extreme positions. So here there is no potential minima and potential maxima, because between the boundaries it is completely free. There is no force acting on it. So it is free, and the potential can be treated as zero. So here, so in this case, the potential of the particle can be treated as zero between these endpoints. Okay, so we can put this x is equal to 0 and this point is x is equal to L. So this v of x is 0 between the x and L. So it experiences some force at this boundary, and since that force would be very large, so we can put some v of x can be infinite. So very large potential energy at the boundaries. Okay, now so between the boundaries its potential energy is 0, so it has only the kinetic energy. So total energy is simply p square by 2m, and that is simply we can write half mv square. Now u is the initial velocity of the wheel, so this wheel can take any value. So u can be any value. So it is a initial speed, and there is no restriction for the initial speed. It can take any value, and therefore e can take any value. So there is no restriction for the energy. There is no discreteness, or there is no quantization for energy if the particle is free particle. So this kind of situation, so this new scenario, we call it is the particle in square well, or particle in 1D walk. Okay, because it is a free particle, because in the sense that it is not experiencing any force between the boundaries. Only at the boundaries it experiences some force. So this particle we call it is a free particle. It is called free particle, and since it is moving only in one direction, it is called 1D. Okay. Now we are going to apply the quantum mechanics into this, and by using the principles of quantum mechanics, we can discuss what will happen to the motion of this particle, or to the energy of this particle, if this particle is a quantum particle. So in this case, it is an uh, classical particle. So in case of classical particle, it can take any energy, there is no restriction. So instead of this wheel, if it is an electron, if there is an electron inside a one-dimensional box, if it is a free electron, or if it is a free proton inside a one-dimensional box, then what would be its movement? What would be its possible energies? Okay, so for that we have to go for quantum mechanics. Okay, so this kind of situation is called the free particle in one dimensional box. Okay, suppose if the quantum particle is confined and one dimensional infinite square well. Okay, so we can redraw the system. So we have consider two walls, so in of infinite height, and the bottom is flat. And suppose you have some electron inside this. So electron is confined, it can move only between 0 to L. Okay, so there is no point of drawing this part here, because it is already understood at 0 we have infinite potential, L we have infinite potential. So this V of x is 0 between 0 and x less than L, and it is infinite otherwise. Okay, so the simple method to solve this equation is we can use the time independence from the equation, because the potential is not a function of time. So by using the time independent Schrodinger equation, we can find out the stationary states, and by knowing the energy corresponding to the stationary states, then we can superpose all the stationary state to find the general solution. Okay, so we have to start with, okay, so I will just copy what we have written here, because these things will we need again and again. Okay, so time independent Schrodinger equation. The time independence from the equation is given as minus h bar square by 2m d square psi by dx square plus v of x psi of x is equal to e psi of x. Now, inside the well, v of x is 0, and so inside the well, if v of x is 0, this Schrodinger equation can be as minus h bar square by 2m d square psi of x by dx square equal to e psi of x, or d square psi by dx square equal to 2me by h bar square psi of x. Okay, so but and there should be a minus sign. Now hereafter I am going to denote this 2me by h bar square as k square, and therefore this differential equation become d square psi of x by dx square is equal to minus k square psi of x. Now this is very familiar differential equations. If you take the derivative of the wave function two times, we are getting the same wave function, except there is a multiplication factor of minus k square. So the solution is very obvious here, because the function which come back to its original form after the second derivatives are the sine and cosine with a negative sign. Okay, if you take the derivative of sine first time, you will get cos. If you derivative cos again, you will get minus sine. So the second derivative of sine is minus sine. So if you take the first derivative of sine kx, you will get k into cos x. And if you take derivative of sine kx again, then it would be k into minus sine of kx, and this k become k square. So it is minus k square sine kx. So if you take the second derivative of sine kx, you will get sine kx with a minus k square outside. Similarly, if you take the second derivative of cos kx, then you will get cos kx with minus k square outside. So this implies that this wave function, it must have two solutions, sine kx and cos kx. So in general, we can write it is a sine of kx plus b cos of kx. So we have two integration constants, capital A and capital B. Now how we can find out this integration constants? So this integration constants we can found from the boundary conditions. because we know that this electron is completely confined in this box. It cannot go outside this one dimension box. So the wave function must be zero outside the box. So if you look at this picture, so now we have found the wave function inside. Now this wave function must be zero outside, because the particle cannot penetrate or it cannot overcome this potential and reach to this position. So for this entire x less than 0, for entire x greater than L, the wave function must be 0. And we know that this wave function must be continuous at every point. So it must be continuous at x equal to 0, it must be continuous at x equal to L. So since wave function is 0 for all point before x equal to 0, and it is 0 for all point after x equal to L, then the wave function must be 0 exactly at x equal to L and as well as exactly at x equal to 0. So these are the two boundary conditions I am going to use. So the boundary conditions, the wave function must be 0 at x equal to 0 and as well as at x equal to L. Now using this boundary condition, it is possible to find the integration constants a and b. So first we can take the psi of x is 0 at x equal to 0. So if you substitute the form of the wave function, so we have formed the psi of x is a sine kx plus b cos kx. So psi of x at x equal to 0 means it become a sine 0 plus b cos 0 equal to 0. So it become a into 0 becomes 0 plus b into cos 0 is 1. So 0 plus b must be 0 or means b must be 0. So which sees that this constant of integration must be 0. So that means we can simply write psi of x as a sine kx. Now we can use the second boundary conditions. Now by using the second boundary condition, it is possible to find the possible values of k. Okay, now we can determine a later by using the normalization condition. Okay, so before going to that, we can discuss the second boundary condition, which is psi of x at x equal to x equal to L is 0. So that means a sine kl must be 0. So that means sine kl must be 0 because a cannot be 0. Because once a is 0, then the wave function will directly become 0. That is not possible. So a must not be 0. It implies sine kl must be 0. Now what is the possible values for kl? So kl can take, is it possible to take kl 0 value? If take kl equal to 0, then the wave function would be 0 for all x, and that is a trivial solution. That is not possible. If electron is present, there must be a non-zero value for the wave function at some point, because uh, if you find mod psi square, it should give the probability density. So if the wave function is 0 for all the points, then its probability density would be 0 at all the points, even though the particles existed. Then that is not physical. So in physical case, the wave function must be present. The wave function must be non-zero at some of the points. So here KL, this K, since K cannot be 0, so the KL cannot be 0. So the second possibility is, in order to make sine KL 0, the KL can take the value pi, or KL can take the value 2 pi. It can take 3 pi, etc. Remember, KL cannot be 0 because KL equal to 0 implies k equal to 0. That implies psi of x equal to 0 always. So this is not permissible. It's not permissible. So kl must be non-zero. So therefore, in order to make sine kl 0, So the KL can take these values, or in general, K can be written as some multiples of pi by L, where N can be 1, 2, 3, etc. So finally, we have got the wave function. So this wave function psi of x is A into psi n pi x by L. Okay. Now, since we have found the value of k, it is possible to find the energy. Now, in this condition is the discreteness condition for k. So k cannot take all values. K must be multiples of pi by L. It is either pi by L or 2 pi by L or so on. It must be integer multiples of pi by L. Now there is a relation between the k and energy. So what was the relation we have discussed earlier? We have already shown that k square must be to ma by h bar square, or E must be equal to h bar square k square by 2m. So we can use this result. So energy is k square h bar square k square by 2m. So it will be h bar square by 2m n square pi square by L square. So finally the energy can be written as n square pi square h bar square divided by 2ml square. So this energy n value can take 1, 2, 3, etc. Remember, n cannot take 0 value. N can take only 1, 2, 3, etc. So the correspondingly the energy can take these values. So the energy become discrete, and therefore the energy hereafter I am going to denote by the symbol E subscript n, because the value of E varies with n. So En is n square pi square h bar square by 2ml square, and the corresponding wave function I am going to denote by symbol psi n of x, which is equal to a sine n pi x by n. Okay, so we have found the psi n. Psi n is the stationary state corresponding to the energy En, or it is the energy eigenstate corresponding to the eigenvalue En, where En is given as n square pi square h bar square by 2ml square, and psi n of x is a sine n pi x by L. Okay, so we have got an important result. So in case of the quantum mechanical system, even a very simple system with no force involved, the particle, the free particle in a one-dimensional box, it cannot take any energy. Its energy is now discrete, or the energies are quantized. So unlike in the classical system, the energies are continuous. It can take any value, like we have discussed the earlier case, that a wheel rolling between two position in the free particle, the free wheel which is rolling between two position. It can take any value depending upon the initial condition, the initial kinetic energy. It can take any possible value. There is no restriction for its speed and as well as its kinetic energy or total energy. But when you're going to apply the same scenario for a quantum system, for a quantum particle, then this entire thing changes. What happens is its energy they become discrete. It cannot take any possible energies. It can take only some definite values of energy, which is given by the relation En, and the correspondingly the wave function, the all function cannot be treated as wave function. So it can take on certain wave function. These certain wave functions psi n are the energy eigenstates, or the wave function corresponding to the stationary state, which is given as a sine n pi x by L. Okay, so next we have to find the values of A, because psi n is A sine n pi x by L. So A is one unknown quantity here. So this unknown quantity we can found from in terms of system parameters, and for that we are going to use the normalization condition. Okay, so normalization, which is if you integrate the modes square of the wave function over the entire distance, it should be 1. Okay, so we know that the wave function is non-zero only between 0 to L. So instead of integrating from minus infinity plus infinity, here we can integrate only between 0 to L. So 0 to L mod psi square dx must be 1 because wave function is 0. Wave function 0 for x less than 0 and x greater than L. Okay, so the wave function is already known to us. So it is 0 to L. It's mod a square sine square kx dx equal to 1. So mod a square, the sine square can be written as 1 minus cos of 2kx by 2. Or to integrate it between 0 to L over dx, it must be 1. So mod a square. So if you integrate this integration, so we have to split it into 2. So 2 can be taken outside. So there will be 2 integration. One is 0 to L dx minus integral 0 to L cos 2kx dx equal to 1. Now what is possible values of k? Remember k is n pi by L. Then we can substitute later. So it become mod a square by 2. The first integration become L minus, if you integrate cos, it becomes sine 2kx divided by 2k, and limit is from 0 to L. This must be equal to 1. So mod a square by 2 L minus, so if you substitute the limit, it becomes sine 2kl minus sine 0. So sine 0 is 0, and what would be sine 2kl? Sine 2kl, remember k is n pi by L, so it becomes sine 2 n pi by L into L. L will cancel, becomes sine 2 n pi, and that must be 0. So that means if you put the upper limit and lower limit, the second term would be 0, and this is simply equal to 1. So this implies mod a square must be equal to 2 by n, or a must be equal to square root of 2 by n. So we have got the value of the constant a. This constant a usually called normalization constant. So finally, the wave function, or the energy eigenstate, the wave function of stationary state, the psi n of x is root 2 by L sine n pi x by L, and correspondingly energy En is n square pi square h bar square divided by 2 ml square. Okay, so we have completed the first part of the solution. We have found the wave function corresponding to the energy eigenstate or stationary state by solving the time independence from the equation. Now the complete wave function must have the time dependent part also. So if you look at the total wave function psi of xt, so psi of xt, a general wave function psi of xt, we can write the superposition of the stationary states. So it is equal to sum over n Cn psi n of x e raised to minus I e n t by 0. So this is the total wave function. So this is the normal algebra to solve the quantum mechanical problem. So first we'll use the time. If the potential is independent of time, then we use time independence from the equation to find the wave function first. The psi n's are the energy eigenstate corresponding to the energy En, which is given as this. Okay, then a general solution can be written as a superposition of the psi n e raised to minus e n t by h cross. So for each psi n, we have a solution e raised to minus e n t by h cross. So this is one possible solution. We can write as psi 1 of xt, and similarly psi 2 of xt can be written as, so psi 1, psi 1, psi 2 of x e raised to minus I e to t by h cross. So we have many solutions, psi 1, psi 2, many time different solutions, psi 1, psi 2, etc. Up to infinity. And if you add all these wave function, that gives the most general equation. So this is the most general equation. Now from this most general equation, the next strategy is, so we have to find the possible values of coefficient Cn, and it is not that much difficult. We have to give the initial conditions for this. So once the initial conditions are given, it is possible to find the possible values of Cn, and we can go further with the time evolution of the wave function. So this is a general approach of any quantum mechanical problem. If the potential is independent on time, we first will find out the energy eigenstate, and we'll write down a general state in terms of the energy eigenstate. Okay, so we'll have an illustrative example of how we can find Cn using one simple example later while discussing the tutorial. For the time being, we are going to stop it here. So in the next class, we'll discuss what are the characteristics of the energy eigenstates of this wave function. So this psi n. So what are the characteristics of this psi n of the free particle in a box? So that is we are going to discuss in the next class. So thanks for watching this video. So see you later. Bye.